Hello, welcome to our webinar, Color Theory and Application for Product Developers, presented by StarRapid. This is a good afternoon for those of you in North America. Good morning for those of you here in China. If you're new to StarRapid, we are a specialized manufacturer of rapid prototypes, rapid tooling, and low volume metal and plastic products. We serve customers around the world. Now, why low volume? Because we help product developers take new ideas from initial concept to prototypes. And from there, we scale up to mass production. Now, we supply parts and assemblies to support a variety of industries. They're as diverse as aerospace, agriculture, consumer products, the electronics industry, medical research, and transportation. We do this via CNC machining, plastic injection molding, metal 3D printing, vacuum casting, pressure die casting, all complemented with a variety of finishing services like painting, plating, anodizing, laser marking, etc. Now, you may be wondering, who is this guy talking to you? So let's meet the presenter for today's webinar. He's a very handsome fellow. Unfortunately, he doesn't look like this. So who am I, this guy? My name is Chris Williams, and I'm the content editor here at StarRapid. Now, I'm not a manufacturing expert, but I am an enthusiast, and I'm also fascinated by the intersection of science, technology, and the mechanical arts. And if you really want to see what I look like, that's me. I like to point at things. Now, if you're at all like me, you're always looking for ways to increase your knowledge about how things work. So today, I'm delighted to be able to present this primer on all you need to know about color for product development, or color theory and application for product development. Now, some of this may seem obvious to you, some not, but I very much believe you're going to learn something that's going to help you to develop your products better, because that's the goal. So let's remind ourselves, what is the goal of this presentation? Why are we offering it? First, because in the world of manufacturing and new product introduction, we've found that all things related to color can be the source of confusion and misunderstanding. This is because designers and manufacturers seem to have different expectations, as well as different ways to measure and talk about color. Now, this can cause production delays and cost overruns, to say nothing of ending up with parts that are not what you want or expected. We therefore hope that the information in this webinar will help you to communicate more effectively with your supplier so you get better results faster. Okay, we in agreement on that? All right, so let's look exactly how we're going to break this down. Here is a general rundown of the contents. We're going to cover 6 main topics. Now, before we begin, please understand that we're going to cover a lot of ground in a short time. So we can really only touch on the most basic aspects of a very complex subject. You will no doubt have questions and comments to make of your own. So by all means, remember to send them to us, and we'll get back to you at the end of our presentation. Now, if I don't have the answer right away, we will have a question and answer session at the end of the formal presentation. If I don't have the answer, I promise I will find it for you, and I'll post it at a later time. Okay, so let's get started. We have properties of color, light, and color temperature. We have human perception and vision, color terminology, color theory, color spaces, and color models, preparing colors for painting, and proper viewing techniques. So, we ready? Chapter 1. Color, light, and color temperature. First of all, the obvious question, what is color? To begin with, what we call color is actually an experience of color. And this experience happens when visible light interacts with your eye and is then interpreted by your brain to form the perception of color. That means color is not fixed, and it's not absolute, but instead it varies with all of these main elements. the light source, the object, the eye, and human perception. We're going to go back to that topic several times in the course of this webinar, so keep that in your mind. It's not a thing, it is an experience. We start with light. What is light? Since the experience of color starts with light, we need to understand a little bit about how light works. Light is, of course, just one small portion of the electromagnetic spectrum, which surrounds all of us all the time. Only that range between ultraviolet and infrared excites a response within the cells of the eye, and it thus becomes light to most of us. Keep in mind, of course, that your light sensitivity may be different than mine, so there is no exact definition of what the visible bandwidth is. We only know an average range, with most people falling in this range. There we have our electromagnetic spectrum. Now, our eyes were made to respond to the sun. Most sighted creatures, including us, have eyes that evolved to respond to the warm light that comes from our sun. The sun's natural light is a very rich blend of many energy levels that can be filtered to reveal a hidden tapestry of almost infinite gradations and complexity. But, of course, the sun is not the only source of illumination in our modern world. We all use many artificial lights every day, and each of these affects the colors we see in the world around us. So, if you want to talk about light in more scientific terms, it helps to know what the color temperature is. So, color temperature. It's a measurement of how hot a black box radiator would need to be for it to glow or radiate at a color equal to the reference color. For example, the bright midday sun has an average color temperature of about 5,500 K. A softer light, more blue, less orange, looks like an overcast sky with a temperature of 6,500 K. This is the common temperature of standardized fluorescent tubes used in light booths. This is what we use all the time. Now, knowing the color temperature helps you because it ensures that two different people working at separate locations you are using equal light sources. Now, this is part, but not all, of the process needed to measure, view, and apply colors in a consistent fashion. So we start with knowing what your color temperature is. We're going to continue to use 6,500 K as the reference temperature for further analysis. How many colors are there? How many colors can you see? We hear questions like these all the time, and the answer really depends on how we define our terms. Let's narrow it down a little bit. Your eyes have photocells that only respond to three major color bands, only three: red, green, and blue. In the most basic sense, other colors are created by combining these three along with the intensity of the incoming light. But it's a bit more complicated than that. If we consider all possible light sources, combinations, energy values, and intensities, a healthy human eye can distinguish millions of distinct colors. Some people say possibly 10 million. And other animals can see colors we can't even imagine, not only in between those wavelengths, but above and beyond the normal visible wavelength of human eyes. All of this depends on our ability to perceive colors. So next, we'll talk about color perception. Remember, we're covering a lot of ground, so by all means, at any point, type in your questions and we'll get back to them later. Thank you. So, human perception and vision, chapter 2. So, we talked about the physics of light and color as natural phenomena. These are kind of absolutes. And we touched on the necessary interaction between the object and the observer. Okay? Now, our ability to experience color is not just dependent on the source of light. There are many other factors involved and they change from person to person. The factors I'm talking about include your mood, the surrounding environment, fatigue, memory, stress, cultural background, your age, many others. Even if you're calm, healthy, and in the right environment to view colors clearly, it's also essential that your eyes function properly. Let's look at how that happens. How do your eyes work? A marvel of engineering, the human eye is a complex mechanism with millions of components working together to enable vision and perception. You want to understand a little bit about how the eye works. This will help to explain how you see colors and also why some people see colors differently than others. For our purposes, we're mostly concerned with the ability of the eye to take in light energy, convert that energy into an electrochemical signal, and then send that signal to the brain for interpretation. This process is made possible by cones and rods that live within the retina. So off we go to the retina. What are cones and rods? The human eye has millions of individual photoreceptor cells called cones and rods, and they perform very specialized functions. Cones are the most numerous, with about 110 million for the average person. There are three types of cones. They respond principally either to green, red, or blue light. Incidentally, we have more green receptors than any other kind, and the reason for that, they think, is because the human race developed in the forest, in the jungle. We needed to be able to distinguish important shades of green if we wanted to survive and if we wanted to find food. We all have about 6 million rods. These cells respond to low light levels. They don't generate color perception, but rather they produce shades of gray, as you might experience on a moonlit night. Okay? So now we know a little bit about how the eye works, but we need to know how good your vision is. Because for all of its ability, everyone's eyes can be subject to error. Therefore, it's important to determine how well your eyes are functioning, especially if you're directly involved in quality control. Now, this is done using standardized color tests, such as what we're looking at now, the Farnsworth-Munsell 100 Hue Color Vision Test, or sometimes just FM100. You can easily find this on the internet if you do a search. It can also be purchased from a specialty dealer. Now, this is the test we use at Star Rapid for all employees, everyone. Only people who score in the 90th percentile or better are allowed to make judgments about product color. And we test everyone at least once a year. Even I don't pass this test. I don't pretend to. The FM100 test can be done online or by using color chips. In either case, the idea is to arrange the tiles from first to last in descending hues. And if you look at the slide carefully, you can see there are very subtle differences from one tile to the next, very subtle. Few people are perfect on this test, but they fall somewhere within a range of values. Again, we only have inspectors who score 90 or above. Now, this shows just how hard it can be for people to agree on subtle differences of hue and shade. Now, in order to talk about the color terminology, we need to learn a few new words to agree on a definition of a few new words. Color terminology. We've established a baseline for understanding color and perception. The next thing we need to do is agree on the terminology we want to use when describing color. These useful color words will help you to communicate clearly about color and its many variations. So first, chroma is a measurement of the intensity or sometimes the saturation of a color. Value is a measure of its brightness. A hue is the base color, and any variation made less intense by adding neutral gray. A tone is a color that's been made lighter with the addition of white. A shade is a color made darker by the addition of black. A tint is a variation of a base color. For example, there are many tints of green, differing from the bright primary green, which is in the center of the green wavelength. It's by taking into consideration these variables that we arrive at the millions of distinct colors that we mentioned earlier. And these terms become very important later when we start to talk about how colors are mixed and prepared when you're actually applying them to a finished part, spraying paint, for example. Tones and shade. Here's an example of how tones and shades work. Now, if you look on the left side pane, we start with the same green base color. On the bottom row, this color gets progressively darker as more black is added. These are shades. In the top row, the green progressively gets lighter with the addition of white. These are tones. I'm going to pause now and take a sip of water. I recommend you do the same. That was good. Specular reflection. When talking about color, we also need to describe how the surface or the substrate affects our perception. This is very important and will become important later when we do actual product applications. So here are a few other useful terms to know. Specular reflection. In the ideal state, light reflects from a flat, smooth surface at the same angle that it came in. In this condition, color and other surface features would appear uniform from all viewing angles. Of course, this is only hypothetical, and perfect reflectivity does not exist, not in this universe. Absorption. Some portion of the light energy is trapped in the material and is usually converted to a lower energy state, meaning it becomes invisible infrared or heat. Even when you have a layer of paint, and we'll discuss this later, on top of a physical object, some of that light energy will pass through the layer. It's not perfectly opaque. It will be absorbed by the underlying substrate and will become heat, and it will distort the reflected light that comes back. That's what we get with scattering. Scattering happens when some percentage of the light energy is reflected off at different angles, which changes its energy level and color in the process. This is the basis for Raman spectroscopy, which uses light to measure material properties. Okay, so now we move on to part 4, color theory, color spaces, and color models. So previously we're talking about the theoretical basis of light, energy, color perception, and color terminology. Now we're going to start applying this knowledge to practical applications that affect how colors are prepared in a manufacturing environment. Okay, there are 2 main ways that colors reach the eye. Additive colors are projected directly from a colored light source, like a computer monitor or a TV screen, while subtractive colors are reflected from an object like a printed magazine cover. I would assume that most of us right now viewing this webinar are using additive colors, watching it on a screen. Additive colors from a monitor are made from red, green, and blue pixels, along with white light, black spaces, to create a composite image that is beamed directly to the eye. Subtractive colors, on the other hand, use a light source, such as the sun or a fluorescent lamp, to bounce the light off of the object and then to the eye. What the eye sees is what's left over after the rest of the light has been absorbed or subtracted. These complex interactions form the basis of color theory and color spaces. What are color spaces? Color spaces are important because by using a color space, it's possible to assign a numerical value to most colors. The industry standard, and this was invented somewhere around the 1940s, for measuring and calibration is called CIE LAB color space, sometimes just called lab space. In this space, the A prime and B prime axes, as you can see in the sphere here, represent specific color values, while L prime is used to express the lightness of the object. Using these reference coordinates, customers and manufacturers now have a clear and unambiguous way to express the intended color for a finished product. Even with a CIE lab value, you need to know how your color is going to be prepared by the manufacturer. And to do that, there are two major color mixing systems or color models for mixing paints, RGB and CMYK. These are color models. The RGB, which is red, green, and blue, color model most closely resembles the gamut or range of colors we perceive in nature. Now, this is the model used by additive sources like computer monitors. This model starts with black and it adds colors to create a final image. CMYK means cyan, magenta, yellow, and the K stands for black. This model is used when mixing paints and pigments. It starts with white and it combines colors that subtract from each other to produce the final look. It has a more limited gamut or range of colors than RGB. Now, this is an important note, and so we're going to pause here to let that last item kind of digest a little bit. CMYK in print form is not the same as RGB on a monitor. Why is this important? Because if you're viewing your reference color on a computer, which is very common these days, you need to understand that the source you're looking at, RGB, cannot be perfectly replicated by CMYK. Many computer programs and apps have digital tools that help to convert RGB values to their nearest CMYK equivalent for printing and mixing purposes. In most cases, we strongly recommend using a reference color chip when trying to match a sample. Also, notice that monitors differ very much in basically the technology behind them, how sharp they are, how bright they are, how precise, what the resolution is in a monitor. So monitors are not a good way, generally speaking, to replicate the color that's going to be applied onto an actual physical object. Reference only, but not for mixing purposes. So instead, we have color chips. These should look familiar to most of you. Pantone and other similar color chipsets, they're used by manufacturers when mixing and matching colors. They offer quick references when it would otherwise be impractical to use a full spectrophotometer. And spectrophotometers can be fooled, so an experienced and professional eye is often preferable. Sample card books are available not only in basic colors, but also pastels, matte, gloss, metallic, chromes, other finishes. They should be kept, this is also very important, in a cool, dry, and dark area to avoid fading, and they should be replaced periodically. At STAR, we replace all of our color books at least once per year. And so an important note, remember, environmental factors will affect these color chipsets, these color cards. Keep them dark, away from UV light contamination. Keep them cool, away from high atmospheric humidity, high temperature. And notice that we also have specialized color chips used for mixing colors for plastic injection molding. This is important because a plastic part in a certain color can still look much different than a printed sample using the exact same color. Let me repeat that. You can use the same base color, but what it appears on a plastic chip or a plastic part and how it appears on a printed piece of paper will look very different to the human eye. Why is this? This happens because plastic is rarely perfectly opaque, but rather it can absorb light just below the surface and then reflect it back with a slightly altered color temperature or color fingerprint. So what the eye sees coming off a plastic chip will be multiple layers or multiple depths taken from the surface of the plastic part and then beamed back to the eye. That will alter the color that you see. In this regard, that's why it's easy sometimes, or happens sometimes, that even a spectrophotometer can be fooled, because it doesn't always read the wavelengths at multiple depths as the eye does. The eye is still the most sophisticated optical instrument. And that's because of refraction, reflection, and absorption. Now, I'm zooming along here. Remember, type in your questions later. I don't want to leave anything undone. If I don't know the answer, as I said before, we'll get back to it later. Now, we've all seen the way that drops of water can distort light beams when they pass through them as well as they bounce off of them. Refracted light passes through, but the pathway is altered or it's slowed down as the light passes through the watery medium. Yes, light slows down. We all think that the speed of light is a constant. The speed of light is a constant in a vacuum, but light does interact with the media through which it passes. Therefore, light passing through water does slow down. This happens in plastic too, which is why it's important to provide a physical sample for comparison instead of just a Pantone number whenever possible. We need to be able to see how the light passes through the medium of the finished part, not just a quantified number from a Pantone chip. These are two very different phenomena, and if you learn nothing else from this webinar, remember this: the practical application for product developers use a physical sample as the best resource for getting the final finished look that you want because of the complex interaction into and through the surface. Okay? Okay. Now, more practical applications. Having these numbers, having samples, how do we begin to prepare colors for painting? First, a sip of coffee. Sip of coffee? Okay. Natural dyes. We now have a common color vocabulary, and we've agreed on a color matching system to apply the color to your parts. This brings us at last to the practical applications, meaning how do we apply painted colors to parts? This is important for product developers, so we'll begin with the basic elements, coloring agents. And there are a few basic types of coloring agents. Dyes. Dyes are highly concentrated organic compounds that are soluble in a liquid carrier or in a molten plastic resin. And they become a permanent part of the substrate. That means they are uniformly dispersed. Dyes have bright colors, but they don't tend to be very robust. They don't stand up to UV light well over a long period of time. Dyes are used for clothing, for example, because they can be absorbed directly in the fibers of the fabric rather than just coating the surface. Okay? Inks. Inks are very fine powders that are dispersed, not dissolved, in a carrier, and they are left behind when the carrier dries. Because they are so fine, ink layers tend to be very thin. We often find inks in printing, lettering, and fine art painting. Obviously, inks are easy to lay over one another because they're very fine and can be very translucent or transparent. Pigments. Pigments are larger powdered organic or inorganic compounds. They are also mixed into a carrier, and they stay behind on the surface when the carrier dries. They make a much stronger film layer, and that's what's used in commercial coatings. So when modern commercial paint manufacturers are trying to create new chemistries for new types of paint coatings, they're working with pigments. They're working with a pigment as well as the sophisticated chemistry of the carriers that will deposit that pigment onto the surface of the coated part. And today is not the day to be discussing the chemistry of coating surfaces, but it is a very complex subject all on its own. Color mixing. Now, understand most facilities, and that includes ours, can't possibly keep on hand every single imaginable color. Even a paint manufacturer doesn't supply every hue and every tint as part of their stock catalog. No one could. Rather, we and many other people, we have a base supply of about 40 main colors, and from which we can mix hundreds of thousands of separate tints, shades, and hues. So in practical applications, if we receive a Pantone reference number or a physical sample, our technicians will mix the relevant base colors to achieve a match. Now, this requires a lot of experience and a lot of testing, as well as a good set of eyes. Now, in a few minutes, we'll talk about how we determine what this sample color is. But before we do that, understand we carefully measure and weigh all the pigments that go into every sample before we approve a color. First, we measure the precise weight of each of the constituent colors, both before and after the color mixing. This data then gives us a ratio, which we record for that specific customer and for that batch. We can then use this ratio in the future if we need to make more of the same color. In practice, it's normally best to spray all of the colors at one time using one batch of color whenever possible. Of course, we also save a sample of the color mix for later reference. And note also that the paint spraying rooms as well as the paint mixing room are kept at a constant temperature and a constant humidity. And that is to make sure that we prevent any contamination inside the paint as it's being mixed and prepared. Paint layers. Almost every painted finish is in fact a series of paint layers built up in various micron thick layers. This is just an example that you're looking at right now. Depending on the application, these can include primers, base coats, color coats, clear coats, and more. Every additional layer will change the look of the finished part. Now, we can't stress this enough. That's because layers are not completely opaque or transparent. They are complex, engineered films with various physical properties, and they absorb, refract, and reflect light in multiple ways. The effects may be subtle, but it's important to note and to account for this when specifying the painted finish on your parts. Again, that's why it may be prudent to give the manufacturer not just a Pantone color number, but an actual physical sample of what the part will look like in the final application, if possible. Now, proper viewing techniques. All right, we've covered a lot of ground so far. We've talked about light and energy, perception and vision, color theory, color models, how to prepare paints in real world applications. Now, this final section is in some ways the most important for product developers. Why? Because unless you're viewing colors in a controlled and repeatable fashion, then it's virtually impossible to get reliable and consistent results when you're working with a manufacturer. This is especially true with a distribution chain in which your manufacturer may be physically separate from you by a continent, by an ocean. You have to be sure that the conditions under which you're viewing your color are the same as the conditions under which the manufacturer has produced it and viewed it and gave a quality assessment. So let's see how we do that. To begin, controlling the viewing environment, we need to look at the light source. Every light source, and we mentioned this before when we were talking about the sun, emits its own characteristic type of illumination. The intensity of the light is measured in candela, while the color of the light is measured according to the color temperature as we discussed before. So candela and color temperature. Most industry standard color booths, for example, use D65, which is daylight 6500K, D65 tubes for consistent viewing. Here is the right way to use a light booth. And before we discuss light booths, if you don't have a light booth and you're a product developer, get one. If you don't have one, borrow one or go to a testing laboratory and use one. If color is important to you, if color is important to your finished product, and you have people really expecting the right color of this finished product, make sure you have access to a color-corrected light booth before you have a sample. Here's the right way to use a light booth. Light viewing booths should be placed in a room away from other bright light sources. This is to avoid light contamination. Whenever possible, inspectors have already had their vision checked for accuracy, just as we discussed before with the FM100 test. Inspectors should wear white or light-colored clothing and have clear, untinted glasses if necessary. Other objects should be removed from the box to avoid distractions. Color samples for comparison need to be placed immediately next to the reference color. It's also a good idea not to stare too long at a color, but to make quick observations, interrupted by periods of rest to prevent eye fatigue. So look at it and then look away. Look at it, then look away. The right way to compare colors. Neutral colored frames may be placed around a sample to separate it from adjacent colors. And we can also do that on physical parts when necessary. We sometimes mask off physical parts when necessary. We also use spectrophotometers. If we don't have a comparison color, we gauge it off of the reading from the machine. Now, we're just about to wrap up our formal presentation. Again, I will check later to see if there are any further questions. I realize we've covered a lot of territory in a small period of time. Let's look at a few of the key takeaways that I hope you have learned from what we've talked about so far. Your experience of color is dependent on the light source, your eyes, your emotional and environmental conditions. Achieving consistent color results is dependent on controlling these variables as much as possible while using a common vocabulary: tint, shade, hue, chroma, etc. Analyzing color is just the first step. The second step is preparing and applying colors in a consistent fashion. So, for the best results in a practical sense, Use this information to help inform your conversation with manufacturing partners and do so early in the product development journey. Once again, to recap, we looked at the basic characteristics of color. We explained the fact that color perception is subjective. We studied the special vocabulary, and we went over the basics of color mixing. Now, we hope that you found this presentation useful, informative, and a little bit of fun. The subject of color and color theory is surprisingly complex, and we've only offered a general overview. With this color vocabulary and a set of techniques, you are now prepared to analyze colors in a uniform and repeatable fashion while communicating effectively with your manufacturing partners. We have more information on our YouTube channel if you're interested in more tips on color matching. And of course, when you're ready to start your next project, we're ready to offer a quotation and expert advice so you get exactly the parts you need. Thank you very much for your time and attention.